Hello there, Mr. Sutton here, bringing you this lesson on rate in, rate out. In this one, we're going to be solving accumulation problems, specifically where we have a quantity that is increasing and decreasing at the same time. For your warm-up on this one, you've got two tasks. First task is to read through all of this stuff and see if you can make some sense of what's going on in this situation. All right, so just to kind of summarize what we read here, we have people coming in an amusement park. We have a rate of entry modeled by the E of t function, and of course people are also leaving the park at the same time, modeled by this L of t function for the rate. And let's see here, the park's open between the hours of 9 a.m. and 23, which is 11 p.m., and at time 9 there's 10 people in the park when it opens because they stayed overnight in the super fancy hotel. All right, task 2 for your warm-up is to figure out how many people have entered the park by 5 p.m. That's time 17. Pause the video and see if you can make sense of this, which is kind of just an accumulation problem like the ones you've been doing up to this point. So, by the way, a good thing to do while you're figuring this out, really any of these problems, if it's a calculator problem, and this one does, whenever I see functions like this, I immediately enter these on my calculator. So take a sec to do that. So here we go. I've entered these under y1 for the E function and y2 for the L function. Now, what do we do with all this? Well, if I want the total number of people who have entered the park, I'm accumulating people entering. Since I have a rate at which people are entering here, I can figure this out by taking an integral of this function. Now, what time period should I use? Well, 17 is definitely going to be my upper limit for this total number of people entered integral. However, how about the lower limit? I'm tempted to say 0, but the park didn't open at time 0 at midnight. It opened at 9 a.m. So we need an integral then from 9 to 17 of the E of t function. And I don't have to write this whole function out because they already defined it for me here. So now I'm just going to do this on the calculator. So I've got the integral from 9 to 17 on here. I got math 9 to do this. And then let me do alpha trace, and I'll pull up y1 because that's where I stored my E of t function. Put in a dx there. And that comes out to approximately, they said, nearest whole person. So that's 6,004 people. For this next part of the problem, they're defining P of t as the number of people in the park at t hours. They want us to find P prime of 17 and explain its meaning in the context of the problem. So pause the video and see what you can do with this one. All right, so if P is the number of people in the park, P prime is talking about the rate at which that number is changing. Well, the rate at which the number of people is changing has to take into account the rate at which they are entering and the rate at which they're leaving. These will both play a role. Specifically, to find the overall rate, we need the rate in minus the rate out. And that's going to give us the overall rate. So specifically on this problem then, we could say P prime of t, might as well define that while we're at it, is going to be E of t minus L of t, which means that P prime of 17 is just going to be E of 17 minus L of 17. So to do this on the calculator, let me pull up my calculator here. I'm going to go ahead and define a third function in y3. I'm just going to make this E of t minus L of t so I can do this all quickly because I feel like I'm going to have to use this again. So that would be, let's see, alpha trace y1 minus alpha trace y2. And now I can just plug things in there and get my derivative. So let me exit out of there. And let me do alpha trace y3 now. And I'm just going to plug in 17 to this and see what comes out of there. So that comes out to a fraction. Let me just do math and then decimal to see what the decimal version of this is. So that's about negative 380.281. So let's now interpret this in the context of the problem. So they're basically saying, what is this talking about? Well, this is the rate at which the number of people is changing. The units on this is going to be people per hour because the rates that it was made up of, E of t and L of t, were also people per hour. And you always have to give a specific time or a time interval on these and explain the meaning problems. So this is the rate at which this number of people is changing at time 17 or 5 p.m. For this next part of the problem, we want to know at what time between 9 and 23 is the number of people in the park the highest. Pause the video, give this one a shot. All right, so if I want to maximize the number of people in the park, I need to figure out critical values for the derivative of that quantity. So what's the derivative of this? Well, that is the p prime of t function that we defined in part B. So I want to figure out where p prime of t has a value of 0. So let me go ahead now and graph out that function, which I conveniently already stored in y3. So here I am on my calculator. I'm going to graph y3 in a moment, but I don't want to graph these other two functions as well. So let me deselect those. Now I'm just graphing my p prime function. What interval? Oh, I'm going to go on the interval from 9 to 23, because that's what they said earlier. So let me do window, and we'll make this 9 to 23. And then let me do zoom 0, zoom fit, just so I get the perfect window on this. And then I'll use my 0 function once I see what this thing looks like. All right, so this is going up, it's going down, it's going up again. We're crossing the x-axis right here. So let me do second trace and do zeros. Move my spider a little to the left, a little bit to the right, press enter one more time for good measure, and that comes out to about 15.7948. And I'm going to call that A. I'm going to store that as A, both in my calculator and on the paper here. Let me go back to my calculator. And I have a feeling I'm going to need this value again, so let me quit out of here. And let me do the store button now, stow. I'll do alpha A. So now I can use that again whenever I want. And I can refer to it as A whenever I want. Okay, so here's a picture of what we just looked at. Now, I want to figure out at what time is the number of people at the park the highest. So there's a few options you have here. If I had a way of figuring out the total number of people in general, I could plug in this critical value along with the two endpoints. That would be my candidates test, and then just pick whichever time gave me the highest value. But I don't yet have a function for the number of people in the park. So I'm either going to have to come up with that function or do this another way. Well, another way I can do this is I see that my derivative is positive on the interval from 9 to a. And I also see that p prime of t is negative on the interval from a to 23. Since I'm increasing until I get to time a, and I'm decreasing after it, logically, point A must be my highest value. So based off of this, we can say that the max number of people in the park has to occur at A hours. For this last part of the problem, they want to know how many people are in the park at the time we found in part C. Well, pause the video one more time and see how far you can go with this one. All right, so in general, if we want to know the total amount of something at a particular time, we need to know the amount that we acquired, the amount of people who came in the park. We have to take away the amount of people who left, the amount out. And there's one other thing we have to take into account, because these two things together just give us the total change from time 9 to time 23. We also have to take into account the initial amount, the people who were in the park when the park opened. So in general, we can say P of A, the number of people at time A, which is when the max happens, is going to be the 10 people who are already there, plus we need an integral from 9 until time A of the following. So we have an integral of the number of people who came in, or the rate at which people are coming in, e of t, and we have to subtract the integral from 9 to a of L of t. That's the total amount of people who left. Of course, you can just put them in the same integral like this. And if I wanted to save even more time, well, e of t minus L of t, we defined that before as p prime of t, so I also could have written just p prime of t in here. Lots of ways to express this. In any case, it's up to the calculator now. So to do this quickly, I've got 10 plus my integral from 9 to, and I'm going to do again alpha a, because that's where I stored my maximizing time. And I stored all of this stuff as p prime of t. I stored that in y3. So alpha trace y3 and a dx. And how many people are in that park at time A? Well, about 3,961 if we round off, and that is in units of people. So, just as amusement parks have to close at some point, so does this lesson. Till next time, Mr. Sutton signing off.